You ever just stop and wonder how your smart home stuff actually works? You tell your speaker to turn on a light, and poof, it happens. Or your thermostat just knows when to kick on. Today, we are going to pull back that curtain. We're going to look at the real secret sauce of the Internet of Things, the interface that connects the digital brain to the real world. So let's imagine a smart sprinkler system, right? You're on your couch, you tap a button on your phone, and halfway across the yard, a sprinkler turns on. It feels like magic, but there's a whole lot going on behind the scenes. How does that digital tap on your screen become actual, physical water on your lawn? Well, that's exactly what we're going to break down.
All right, so at the very heart of every single smart device, you've got this little guy, the microcontroller, or MCU for short. And you've got to think of this as the brain of the whole operation. It's basically an entire computer squished onto one tiny chip, like the ESP32 you see in so many projects, and its whole job is to run the code and call the shots.
So what makes this brain tick? Well, it's got I/O ports. That's just its way of talking and listening to the outside world. It's got memory to store the instructions and remember stuff. It has a clock speed, which is basically just how fast it can think. And of course, for anything Internet of Things, it absolutely has to have Wi-Fi or Bluetooth to get online and talk to your phone. That part's non-negotiable.
Okay, so we've got the brain, but a brain isn't much good if it's just sitting in a dark box, right? It needs to know what's going on in the world. It needs senses. And that's where sensors come in. They're the eyes, the ears, the fingertips of the device. They take real-world stuff, like how wet the soil is or how bright the room is, and they turn it into an electrical signal the brain can actually understand. And, not all senses are created equal. They basically come in two flavors. You've got active sensors. Think of these like a bat using sonar. They send out a little pulse of energy, light, sound, whatever, and then they measure what bounces back. Then you have passive sensors, which are way more chill. They're more like our eyes. They just sit back and detect the energy that's already there, like heat or sunlight. And because they're not sending anything out, they use a lot less power.
All right, we've got a brain to think, and we've got senses to feel. What are we missing? The ability to actually do something. And that, my friends, is where actuators come in. These are the muscles of the operation. They're the part that takes an order from the brain and makes something happen in the real physical world. Spinning a motor, flipping a switch, you name it.
Now, these muscles can be all sorts of things. But for our smart sprinkler, the muscle is going to be a relay. And I love this analogy. Think of a relay as a tiny electronic bouncer at a club. The brain sends a tiny little signal, that's like whispering the secret password. The bouncer, our relay, then opens the big velvet rope to let the high-power circuit come through. In this case, that's our heavy-hitting 12-volt water valve.
So brain, senses, muscles. Seems simple enough, right? Let's just plug them all together, wire them up, and call it a day?
Yeah, if only it were that easy. This is where we hit our first and honestly our biggest roadblock, and it's where all the really clever engineering comes into play.
Here's the deal. They don't all speak the same language. And in the world of electronics, language is voltage. Just look at this. Our brain, the ESP32, it's thinking and talking in a nice, calm 3.3 volts. But a lot of our common sensors, they're operating at 5 volts. And the muscles, the motors and valves, they might need 5 or even 12 volts to get the job done. It's a total mismatch. They literally can't talk to each other directly.
And let me be perfectly clear. This isn't just a simple misunderstanding. This is a huge deal. If you try to scream with 5 volts into an ear that's only built for 3.3 volts, you're not just going to get static. You are going to blow its eardrum out. I mean, you will literally fry the microcontroller. Poof, game over. Permanent, irreversible damage.
So what do? We need a translator, right? We need some kind of electronic bridge that can safely connect these different voltage worlds. And that, right there, is the hero of our story today, the interface circuit. This is the magic little piece of engineering that allows the brain, the senses, and the muscles to all work together in harmony.
Okay, so let's pop open our toolbox and see how we build these bridges. Our first tool is incredibly simple, but it's also super elegant. It's called a voltage divider. This is what we use when our little brain needs to listen to one of those loud 5-volt sensors. It's just 2 resistors, but together they basically act like a volume knob, turning that 5-volt signal down to a nice, safe level the MCU can actually handle.
And here it is in action. This is straight from the source schematic. You can see the 5 volts coming in from the sensor. It flows through those 2 specific resistors, and what comes out the other side? Just 2 volts. That is a perfectly safe, gentle signal for our 3.3-volt brain to read. The message gets through, no one gets hurt. Problem solved.
Okay, so that's how the brain listens. But what about when it needs to talk?
How does its quiet little 3.3-volt voice command a big, powerful muscle? For that, we pull out our next tool, the transistor. The best way to think about a transistor is as a tiny electronic gatekeeper. Our brain sends a little 3.3-volt signal to the transistor. That signal is just enough to tell the gatekeeper to open a massive gate, and when it does, a whole separate, powerful current, maybe 5 or 12 volts, can rush right through to power our muscle.
And if we look at the schematic, we can see exactly that happening. See that component labeled Q8? That's our transistor, our gatekeeper. The ESP32's brain sends its little signal there, and Q8 just flicks the switch for a much beefier 5-volt circuit. The brain is telling the bouncer what to do, and it just works. It's elegant. Now, for our third tool, this one is just awesome. If you want the absolute max level of safety, you use something called an optocoupler. Get this. It creates a literal air gap for electricity. There is no wire connecting the two circuits. Instead, the brain turns on a tiny little light on its side. A beam of light shoots across a gap inside the chip, and a light sensor on the other side sees it and activates the high-power circuit. It's communication with light. There is zero electrical connection. How cool is that?
Back on our schematic, that chip labeled U1, it's a 4N35, that's our optocoupler. It's using that little light beam trick to build a complete firewall between the sensitive little 3.3-volt brain and the noisy, high-power 5-volt circuit. You just can't get any safer than that. It is total electrical isolation.
So let's put it all together and trace the entire journey one more time. Ready? First, a 5-volt sensor senses that the soil is dry. A voltage divider bridge scales that signal down safely. The 3.3-volt brain thinks about it and decides to water the plant. It sends a tiny 3.3-volt signal to another bridge, a transistor or an optocoupler. That bridge then activates the muscle, or relay, which finally switches on the heavy-duty 12-volt water valve. And boom, the plant gets watered. Sense, bridge, think, bridge, act. That is the entire loop.
And that's really the secret, isn't it? The magic we talked about at the beginning isn't really in the app on your phone or some code floating in the cloud. It's right here, on the circuit board. It's in these clever little hardware interfaces that act as translators, bridging the gap between the digital and the physical, and allowing a tiny computer chip to make a real difference in the world around us.
So now you know the fundamental recipe. You've got the brain, you've got the senses, you've got the muscles, and most importantly, you know how to build the crucial bridges that connect them all. So the only question left is, what are you going to build? What problem are you going to solve? Because once you understand these basic blocks, the possibilities, they're truly endless.